Okay, this lesson is now on chapter 1.2, still on Emaths, but this time we'll be going to be talking about zero and negative integral indices. Okay, so let's okay, the next law we want to talk about is what happens when the power equals to 0. What does it exactly mean? So there are a few ways we can explain this. You can read through the class activity 4 and fill in the blanks on page 8 by yourself to find out what does a to the power of 0 give us, where a can be numbers such as 2, 5, 10, so on and so forth, except for 0. Okay, so what happens when it is a power of 0? I'll show you another way. Let's consider a to the power of 1. Okay, this gives us simply a. What about a power 2? This gives us a times a. What about a power 3? We have a times a times a, right? And let's try and understand what happens when we move backwards. What are we doing over here? When we move backwards, we see that the number of times we multiply by a reduces by 1. So it is actually a division of a, isn't it? So over here, it is a division of a. Another division of a. Another division of a. So then what actually happens when I have a power 0 equals to, okay, let's leave this as a blank first. A power 0. So if we follow the same pattern, we should be dividing by a. This time, when I divide by a, what will I get? I get 1. So regardless of the value of a, I have the value equals to 1 as long as the power is equals to 0. So this is one way we can do it to prove it. Another way is, like I mentioned, class activity number 4 on page 8. Okay, so our next the next law that we need to know is that a to the power of 0 equals to 1. Okay, you can use our calculator to verify this also. Simply key in, for example, 3 power of 0. Your calculator will tell you it is equals to 1. What about 99 to the power of 0? Your calculator will still tell you it is equal to 1. Okay, so next, let's talk about on page 9 we have 2a. Okay, we're given 7 to the power of 3 divided by 7 to the power of 5. So we know that we can write it this way: 7 power 3 over 7 power 5. And we know from our laws of indices, we have 7 power 3 minus 5, which is actually 7 to the power of negative 2. What exactly does this 7 power negative 2 mean? Okay, so let's try and think about this question in another way. 7 power 3 divided by 7 power 5. Again, I've got 7 to the power 3 over 7 power 5. Notice that the steps are the same. But now, instead of applying my laws of indices, let's have 7 times 7 times 7 in the denominator. 7 times 7 times 7 times 7 times 7. Okay, so there are 5 of them. And of course we can cancel. So use your pencil. Cancel, cancel. Oh, what are we left with? 1 over 7 squared. Okay, so since we started with the same question, 7 power 3 divided by 7 power 5, and we didn't make any mistake, this of course tells us that 7 power negative 2 is the same as 1 over 7 squared. Okay, you can try filling in the blanks for 2b. Okay, on page 9, question 2b. And you should see that a to the power of 4 divided by a to the power of 7 equals to a to the power of negative 3. And it is also the same as a to the power of 4 divided by a to the power of 7 equals to 1 over a power 3. So this tells us that a power negative 3 equals to 1 over a power 3. And then combined with what we saw earlier, 7 power negative 2 is 1 over 7 squared. I think we can conclude that, in summary, a power negative n equals to 1 over a power n. Okay, this is the next thing that we need to know. Okay, then you may move on to example 5. Read and understand example 5. Do, try it 5. Likewise, example 6 and do, try it 6. Okay, these are your homework questions for exercise 1.2. Take note, for question 1, it is to be done without using calculator. For question 2 and question 3, you are supposed to be using positive index notations, which means none of the powers are going to be negative. All of them must be positive. So for example, if we end up with an answer such as c to the power of negative 5 d to the power of 4, we will need to simplify. We will need to rewrite this as d to the power of 4 over c to the power of 5. These are positive index notations. Okay, now let's move on to 1.3, fractional indices. So far, for the powers that we have been dealing with, they are either positive integers or negative integers or 0. But what happens when the powers are now fractions? Can it be done? Can the laws of indices still be applied? The answer is yes, they can still be applied. So let's go on to page 13. You can read page 12 yourself. There's some basics we should learn in lower secondary already. I just want to focus on the next part. A to the power of half times a to the power of half. Okay, and we recall that our laws of indices told us that a power m times a to the power n is supposed to be a power m plus n. Okay, so here we have a to the power of half plus half, which is a to the power of 1, which is simply a. Okay, then we also know that a to the power of half to the power of 2. Again, our laws of indices, a power m power n is a power m n. So this gives us a to the power of half times 2, which is a to the power of 1, which is simply a. Okay, all these, they mean the same thing. Then, if because over here I have a something square equals to something. Okay, so let's consider this. If I have x squared equals to, for example, 9, this tells me that x equals to plus minus square root of 9, which is plus minus 3. Okay, so similarly, we are going to be able to write that a power half, it must be equals to the square root of a. Okay, you may be wondering why there isn't a negative, why isn't there a plus minus, why am I just taking the positive value? So you read what is written on page 13 under section B, the first sentence. Okay, so here we have a to the power of half is actually equals to square root of a. Next, let's talk about a to the power of 1/3. A to the power of 1/3 times a to the power of 1/3. Here, by having them multiplied to each other 3 times, we know that the final answer must be a to the power of 1, which is simply a. So then what does just one of it mean? This must therefore be the cube root of a. Okay, because the same thing multiplied by each other 3 times, we are actually taking cube, the cube of a to the power of 1/3 is equals to a. So if we work backwards, a to the power of 1/3 must be cube root of a. So in summary, we say that if a is positive and n is a positive integer, our summary is this: a to the power of 1/n equals to the n root of a. Okay, so examples: a to the power of 1/9 must be the 9th root of a. A to the power of 1/100 must be the 100th root of a. Okay, so next we also can consider a to the power m over n. So this is a fractional power again. We can separate this out to become a to the power m power 1/n. So this was one of our laws of indices. We saw that a power m n actually equals to a power m power n. Okay, which is actually the same as a power n power m. So the powers can just be multiplied together like this. So m times 1/n, of course, is going to give you m over n. So this is an example. So now we have this fractional power 1/n again, which implies that it is the nth root of a power m, right? Okay, so this is something you need to know and be familiar with. You will be tested. Alternatively, we can also say that a power m over n equals to a power 1/n power m, right? So the powers over here multiplied together will still give you the same fraction. Only thing is that this time we are rewriting it as a power 1/n, which is actually the nth root of a, then the whole thing power m. All of them are the same. So in summary, this is what we have. A power m over n is actually equals to the nth root of a power m, which is actually the same as nth root of a power m. You can choose to substitute values inside and convince yourself that it works. So as per our routine, you are supposed to read and understand example 8 and 9. Do try 8 and 9. And our homework for exercise 1.3. So this is your homework for exercise 1.3. It is due on Friday. Okay, 18 Jan. That is because your exercise 1.2 is due on 17 Jan. So one day for each of these exercises.